Hello student, in this lecture I will discuss about Routh stability criteria. Basically I will discuss about stability criteria, or we will discuss how we will find stability of a system by using Routh stability criteria. Okay, so let's start our discussion. In previous lecture we have discussed that for a system to be stable, if all the poles of the system must lie in the left half of S-plane. For second order system, one can find the poles of the system by using hand calculation. But for higher order system, finding the location of pole is a very laborious process. So, the Routh-Hurwitz stability method provides an answer or provides a solution to this problem. Okay, so let's see. To determine the number of roots having positive real parts for a polynomial. So first case is, consider a first order characteristics equation expressed by given polynomial, which I have mentioned here in equation 7.2, that is a0s plus a1 equal to 0. So the roots of this equation is s equal to minus a by 0. Okay, this is first order system. Now we consider second order characteristics equations. So our second order characteristics equation is this, which I have given the equation number 7.3. This is actually a0 s square plus a1s plus a2 equal to 0. So the roots of this equation are, there are two roots because this is second order characteristics equation. So roots are s1 and s2, and this is equal to minus a1 plus minus root under a1 square minus 4a0 a2 divided by 2a0. So it is observed that for the real parts of both the roots to be negative, the coefficients a0, a1 and a2 should be either positive or of same sign. Thus, if all the coefficients of a first order and second order polynomial are either positive or of same sign, then it is concluded that the roots of the polynomial does not have a positive real part, and a control system whose characteristics equation is expressed by such a polynomial is stable. Now consider third case. So see, the requirement that all positive coefficient or same sign coefficient is not sufficient for ascertaining the stability of a control system whose characteristics equation has an order higher than 2. A clarification of the above statement is supported by an example of this third order characteristics equation. So here we have taken third order characteristics equation for clarification of this statement. Okay, so we consider this equation, that is s cube plus s square plus 5s plus 125 equal to 0. So on factorization of this equation is expressed by this s plus 5 into s square minus 4s plus 25 equal to 0. So this is third order characteristics equation. So obviously there are three roots. So roots are s1, s2 and s3. So first root, that means s1 is equal to minus 5, s2 and s3 are plus 2 plus minus j 4.5j. Okay. So see, although all the coefficient of the third order equation, that means the equation number 7.4, this is third order characteristics equation. So see, all the coefficient of third order equation are positive, and the equation has distinctly two roots S2 and S3 having positive real parts, which makes the system unstable. Okay. Now consider another third order characteristics equation is s cube plus 4s square plus 6s plus 4 equal to 0 and given the equation number 7.6. Now on factorization of this equation we can write s plus 2 into s square plus 2s plus 2 equal to 0. So the roots there, this is third order characteristics equation, so obviously there are three roots. So first root is minus 2 and second two roots are minus 1 plus minus j1. So it is observed that none of the roots of this equation, that means 7.6 equation, have positive real parts. Therefore the system is stable. Hence, for determining stability of higher order system, in addition to aforesaid necessary condition, a sufficient condition is further needed, and this sufficient condition is given by Hartois. That means Hartois is the name of the scientist. So this sufficient condition, that means for determining the stability of higher order system, in addition to aforesaid necessary condition, a sufficient condition is further needed, and this sufficient condition is given by Hartois determinants as like this. Okay, so see Hartois determinants of a polynomial. Okay, so here we consider this equation, that means this is general nth order equation, nth order system characteristics equation. Okay, so equation is a0 s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2, like this. This is to a to the power n and this is equal to 0. Okay, so see, for the roots of the nth order polynomial to have only negative real parts, that means all the roots to lie in left half of S plane. Okay, and it is required that the polynomial's Hartois determinants d suffix k, where k is 1, 2, 3 up to n, be greater than 0. Okay, so for the roots of the nth order polynomial to have only negative real parts, and it is required that the polynomial's Hartois determinants dk be greater than 0. So Hartois determinants are given by d1 is equal to a1 and this is greater than 0. d2 is represented by this matrix and this matrix obviously greater than 0, and d to the power n, like this, d to the power n is obviously expressed in this matrix. Okay, and this dn obviously greater than 0. Okay, so for evaluating Hartois determinants mentioned here, lot of time is involved. However, in relation to evolution of Hartois determinants, Routh has simplified the procedure for ascertaining the number of positive real part roots of a polynomial, and the method is called Routh-Hartois criteria. Okay, because for evaluating Hartois determinants mentioned here, lot of time is involved. So, however, in relation to evolution of Hartois determinants, Routh is another scientist. Okay, Routh was another scientist. So, however, in relation to evolution of Hartois determinants, Routh has simplified the procedure for ascertaining the number of positive real part roots of a polynomial, and the method is called Routh-Hartois criteria. Okay, so see Routh-Hartois criteria. So see, in order to determine the existence of a root having positive real part for a polynomial equating in order to determine the existence of a root having positive real part for a polynomial equation is this: a0 s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 up to a to the power n, and this is equal to 0. Okay, so here two rows consisting of alternate coefficient of polynomial 7.10, that means this equation, this above equation I have given, the equation is equation number is 7.10. So see, in order to determine the existence of a root having positive real part for a polynomial equation is given this, which I have mentioned in equation number 7.10. Okay, so now two rows consisting of alternate coefficient of this polynomial, that means of equation 7.10's polynomial, are formed as like this. That means this one. So two rows consisting of alternate coefficient of polynomial 7.10 are formed like this. Okay, a0, a2, a4, a6, and second rows is a1, a3, a5. Okay, now the following array is formed. Okay, so here I have considered sixth order polynomial. So the array is formed like this. Okay, now see, in the Raoult array, with the array I have given the equation number 7.11. So this array is called Raoult array. Okay, so in the array, that means this is our Raoult array. Okay, so see, in the Raoult array 7.11, the coefficients b1, b3, b5, c1, etc. are related to the coefficient of the polynomial 7.10 like this. Okay, so what is b1? Actually, what is the relation between b1, b3, b5, c1 to the coefficient of the polynomial 7.10? So b1 is equal to this, b3 equal to this, and b5 equal to this. Okay, and c1 is equal to this, and d1 equal to this. Okay, so from this array, that means here I have given the Raoult array. I have given the Raoult array 7.11. This is the equation number. So from the array 7.11 formed, it is observed that the elements of the first column are related to Hurtway's determinants. For like example, b1 equal to d2 by d1. Okay, so from the array formed, it is observed that the elements of the first column are related to Hurtway's determinants. Okay, so the number of changes of sign in the first column elements of Raoult array gives the number of positive real parts of the polynomial. Okay, so the number of changes of sign of the first column, that means first column means this column. This is our first column. So if there is sign change, that means the number of sign change indicates the number of roots present in the right hand side of the S-plane. Okay, so see, the number of changes of sign in the first column elements of Raoult array gives the number of positive real part roots of the polynomial. Therefore, for a stable system, there should be no change of sign in the first column of Raoult array formed from the coefficient of the characteristics equation expressed in polynomial form. Okay. So see, while applying Routh-Hurwitz criteria, it is imperative that no powers of S in the characteristics equation be absent. Any absence of such powers indicate the presence of at least one positive real part root and confirms system instability by inspection. Okay. So, while applying Routh-Hurwitz criteria, it is imperative that no powers of S in the characteristics equation be absent. Any absence of such powers indicate the presence of at least one positive real part root and confirms system instability by inspection. Okay. However, if the characteristics equation contains either only odd or even power of S, this indicates that the roots have no real parts and possess only imaginary parts, and therefore the system has sustained oscillation in its output response. Okay. So, if the characteristics equation contains either only odd or even power of S, this indicates that the roots have no real parts and possess only imaginary parts, and therefore the system has sustained oscillation in its output response. Okay. Now we will discuss about drawback of this Routh-Hurwitz criteria. So following difficulties are, so see, these difficulties are faced while applying Routh-Hurwitz criteria. First is the element in one of the first column of Routh array is 0, and second is all the elements in one of the rows of Routh array are 0. So these two conditions I will discuss in example. That means when I will give example of Routh stability criteria, that time I will discuss these two problem. Okay. So in summary, I will tell there are two conditions in Routh-Hurwitz criteria. The first condition is necessary condition for a system to be stable, and second condition is sufficient condition for a system to be stable. So what is necessary condition? So necessary condition is, first is in necessary condition, first point is none of the coefficient of the characteristics equation should be missing or 0. So if there is any coefficient is missing in characteristics equation, then we cannot analyze, or we cannot analyze stability by using Routh criteria. Okay. And second condition is all the coefficients should be real and should have same sign. Okay. So if these two condition is satisfied, then we go then we can analyze the stability of the system by Routh-Hurwitz criteria. So this is necessary condition, and if necessary condition is satisfied, then come to the sufficient condition. So sufficient condition is all the terms in the first column of Routh array or Routh tables should be positive and should have the same sign. So if there are two necessary condition, first is necessary condition, in necessary condition first is none of the coefficient of the characteristics equation should be missing or 0. Okay. So if any coefficient are missing in the characteristics section, then we cannot analyze the stability of system by Routh criteria. And second necessary condition is all the coefficients should be real and should have same sign. Okay. So if these two condition is satisfied, then come to sufficient condition. So sufficient condition is all the terms in the first column of Routh array should be positive or should have the same sign. So this necessary condition and sufficient condition are satisfied, then we say a system is stable by using Routh criteria. Okay. Now in the next lecture we will discuss some example based on Raoult stability criteria.